This video talks about the built-in function that MATLAB has for solving nonlinear equations. Within this set of videos, we discussed various methods in order to solve nonlinear equations. So we discussed the bisection method, which is a bracketing method. We discussed the Newton method, an open method, and the closely related secant method. Also, we took a look into how these methods are implemented in programs, and also in the homeworks, you're asked to perform some basic implementations or some basic modifications of these methods. And it is important to state that implementing such methods is part of the learning experience. So really getting your hands dirty and doing this stuff by yourself is a learning experience. However, when you are encountered in the real world with a numerical problem, I strongly suggest that instead of implementing a new method or something you find in a book, you look at what is out there, what is pre-implemented in the software that you're using, because there might be very good and general use implementations which are applicable to many problems. They might be available in your software package that are very robust. For instance, they catch certain exceptions of certain properties of functions that would make the program crash otherwise. They could be very fast or optimized, making use of specific hardware such as GPUs or parallel architectures. And all these things, implementing them yourself could take a lot of time and is probably not worthwhile if you're just trying to solve a certain problem. And this is kind of a balance between not reinventing the wheel, as seen here in this cartoon on the left, or trying to perfect the wheel for your specific application. So if you have an application which is actually very computationally demanding and you have a strong indication that, for instance, a very specific implementation of a certain algorithm that you can do, that you have to implement by yourself is worthwhile, then by all means check it out. If not, if you're just looking to solve a problem and get on with it, I really strongly suggest that you look at built-in functions in MATLAB or in Python or whatever you're using. And this is not only the case for solving nonlinear equations, but this is an advice in general for any type of computational problem. Let's give a brief overview of the methods that we looked into so far. So we discussed the bisection methods, which is a bracketing method, which encloses it constructs an interval in which the solution to the nonlinear problem is contained, and it tries to reduce the size of that interval in every iteration. And this is how it can be programmed mathematically. It always converged, and it's quite cheap, but very slow convergence, linear convergence. On the other side of the spectrum, we had Newton's method, which is an open method. It uses the first derivative as well as the function value at the current solution in order to update the solution for the next iteration. And by doing this, this can be very fast. If some certain conditions are met and we're close to the actual solution, well, then we have quadratic convergence. And that's extremely fast convergence in which the amount of digits that you get correct basically doubles in every iteration. So that's very fast. The downside is mainly that it's not very robust and can be highly sensitive and tends to diverge for bad initial conditions, let's say. A kind of midway approach here was the secant method, which allows you to approximate this derivative using a secant line, which makes it a bit more computationally efficient per iteration. It tends to be more robust. It's faster than bisection, but it's not as fast as Newton. So we have superlinear convergence, not quadratic convergence. And there is also no guaranteed convergence as in the case of bisection. Now, MATLAB has a built-in function which combines many of the properties of the previous methods, and that's the F0 function. and it can simply be called by using f0. You give a function to this a function handle to this function f0 and a certain initial guess, and that will solve or try to solve this nonlinear equation f of x is equal to 0. For this, it uses what is called as Brent's algorithm, and it consists of two main steps. At first, it brackets the solution, so it tries to find an interval which is guaranteed to contain the solution, and then it tries to compute the solution within that bracket using either the bisection method, which is guaranteed to converge, or using the secant method or a variation of the secant method for improved convergence rates. So based on certain conditions, it switches between these two methods and is hence optimized for both stability and speed. This is slightly slower than Newton. So the convergence is not as fast as Newton. It's not quadratic, but it can be superlinear. And also importantly is you can throw a lot more functions with a lot more crude initial guesses at this f0 function, and it will still solve it. So it's much more practical than Newton's method. Let's take a look at how we would solve the circle segment problem using this f0 function. Just a brief recap. This is the nonlinear function which we want to find the zero of. So we want to find theta such as this is 0. And this corresponded to this geometric problem where we try to find the theta such that for a given AS and a given R, this geometrical picture works out. Now, how do we call this? Well, you can set certain options for the solver. These are optional. Otherwise, it will revert to certain default settings. But here I chose to set the display option to iter, which means that it will display information about all the iterations such that we can see what it's actually doing. And I set the tolerance on the solution to a very strict value, just to have it compute until a very accurate solution. And then calling f0 is actually as easy as just providing here this function handle. So if you're not familiar with the syntax, look into Appendix A1 of the textbook. I give an initial guess of x is 3, and I make sure that it takes into account these options. If you run this in MATLAB, then the output will look like this. And well, we clearly see that there are two phases here. So first it does a bracketing phase where it tries to find an interval containing 0. So I did not give already in advance such an interval. It tries to find it by itself. And how does it do that? Well, it is provided with an initial guess of 3. And then it says, well, in the initial case, f of a is negative. And then it successively updates both a and b up until the point where it finds a point where here in this iteration, it has found a and b such that f of a and f of b are different in sign. So the program knows now that there is a 0 in between 2.32 and 3.48. And this took 14 function evaluations. Okay, so now that it has identified such an interval, it will increase the accuracy by using either bisection or the secant method, or this quadratic inverse interpolation method, which is kind of a improved version of the secant method with a slightly better rate of convergence. And we see that, well, it starts at one of the edges of this interval, and quite fast after a couple of iterations it attains this value where it finds that the function value is actually 0, so it converges to the exact solution in this case. It also gives us an output here, the method that it used. And we see here that it only used this inverse quadratic interpolation scheme and no bisection methods were necessary. So if it's possible, then it will always use the faster methods and not the bisection method. So this clearly shows that, well, this is a very smart tool. It will first try to guarantee that a solution exists, and then it will try to close in on this solution using optimal and fast methods to improve the accuracy.